Now.
All right, well, we'd like to welcome everybody to the presentation we're going to have today. We're very excited about it. This is going to be a very new kind of experience. We're going into a Google Hangout session with MUFON. It's one of the first times we've attempted to do this. We're doing it between two states. Actually, we're up here in Alabama. My name is Rich Hoffman. I'm the state director of Alabama and Mississippi. We're holding our meeting, and we have as a guest speaker Mark D'Antonio, and also connecting in with the Florida MUFON group in Southwest in Fort Myers area, and we're glad to have them on board. So, welcome, Mark. We want to thank you for joining us. Mark, to let you know a little bit about Mark, Mark is a CEO of his own company called FX Models. He helps to create a variety of models. In fact, just want to point out to everybody in this group, he has models in the Davidson Center and over here that he's put together, models of planets and various other kinds of things. He's also put together a school that was nearby here. He also built models for that school of planetary systems, and he does that. He does special effects and has played a part of a lot of roles in a lot of working with producers who create special effects in movies. He's also, from the UFO standpoint, he's MUFON's basically chief photo and video analyst. So he gets all those wonderful photographs that we submit in for UFOs. In addition to that, we looked at him. He's got a great background in astronomy. I believe his degree is in astronomy, and he's spent lots of time going and looking at sky photos at various observatories, and he gets these really incredible graphics that we're going to get to see some of them here today. He's going to be speaking to us about exoplanets, and the topic here is called the Populated Universe. That was his presentation title, and we're looking forward to it. And Mark, have at it. Welcome.
Hey, thank you so much. First of all, we just want to go through the housekeeping, make sure that everybody can hear me clearly. Make sure that everyone can see the presentation on their screens.
Yeah, we're muted.
So, Morgan, at your end, do you have the presentation up and visible yet? He's laughing. That means no. How about you, Rich? You're all set to go. People are waiting for me at your end, I'm sure.
I am ready and willing.
Okay. All right. Well, this title slide stays up for a few seconds anyway, so Morgan has time to get the presentation up. One of the things that we'll start with is that, first of all, I'm gonna mute Morgan from my side. All right, and I'm gonna leave you live, Rich, because I don't hear you through the mic right now. But what I want to talk about is when I was there was a time when I was interviewed by a web magazine. And one of the things that they said to me was that, what did you do? How did you get started? And they explained that I was a photo analyst and my degree is astronomy and so forth. But one of the things that was important was listening to people's responses later. And one of the things I heard was they said, you know what, this guy, you're half scientist, half crackpot, half geek. I don't mind being 1.5 people. But what was funny was that I ended up having to say, well, I kind of take issue with that. I'm not a scientist per se. Okay, you can call me a crackpot, you can call me a geek. We deal with that. You know, the media always portrays the people that believe in UFOs or look for UFOs as the tinfoil hat.
Like your cookies.
And that's something
everything.
that
so strange.
We don't want to participate in anymore. We want to show them that there's a way past that. Well, for me, the way past that is science, and that's what this is all about. The Populated Universe is also the name of my book, but don't worry, I'm not here to plug the book. But I am trying to show you that using science, we can actually show the real, true, plausible reasoning and defense of our belief that alien beings could not only exist, but have traveled around the universe and maybe mapped it out quite extensively. It's very possible.
Now? What is this?
So,
look at this.
I'm also
what
hearing
is
Morgan.
going on?
I gotta mute you.
What in the world is going on?
Anyway, so what happens is when we talk to the media, one of the problems we have is trying to get them to listen to us from a scientific point of view. That's very hard. And you know, in the defense though, okay, of how we're being treated as the tinfoil hat crowd, there's a lot of good fakes out there, a lot of good Hollywood movies, a lot of good, a lot of good people that can actually make these fake movies so well, and they do these CG renderings so well. And there's also a handful of really colorful characters that have a vested interest in UFOs, and so those sometimes help us, sometimes don't, and that's a problem for us. We can't always guarantee their honesty, but that's why if we stick with science, we can actually pursue the truth, and it's unbiased, it's not opinionated. Facts don't have an opinion. They are just facts. They stand alone.
Did you try putting it back on movies?
This is very important to us, all right? So that said, I want to push forward here because, we've seen a lot of these movies, Star Wars, Close Encounters of the Third Kind, they're mostly fanciful, but some offer fearful visions like Alien and Battle Los Angeles. There was a weirdly robotic race that comes from another world to conquer us. District 9, one of my favorite movies, was actually about cast-offs from another alien society that made their way here. If you haven't seen that movie, that's one to watch because that's phenomenal. I really like that movie. It has a great message. So when we look back and we think about this, in our culture, the earliest genuine sighting was, of course, the Kenneth Arnold sighting. He saw 9 saucer-like objects at Mount Rainier, and the problem was that was basically what he saw. There was, there was no real physical evidence. We never grabbed a saucer. We didn't see anything that could actually, show absolute proof. What that did was, is pave the way for setting the tone for later disbelief amongst the media and other people. And in Roswell, it had happened. There was early evidence that, in Roswell, the early evidence was that, there was a saucer, but then the papers later came out with another story, as we'll see in a minute. Then there's cases like Billy Meyer. Now, his photos were classically wrong. And for those of you that believe in Billy Meyer, take heart, because I have something else to say about this. There were clearly toy cars used in his photos. The photos were recreated or created in a way that just, looked like they were created with small models, and we could prove that, in fact. His wedding cake ship in front of the house, clearly made from parts in his barn. The base, in fact, was the top of one of his feed barrels, right down to the ridges and the lip on the barrel that you could clearly see in the model, that he photographed as a ship. There was no attempt made to really disguise it. But here's my point. That doesn't mean he didn't experience something. What happens is, because people aren't believed, because their stories are only anecdotal, sometimes they manufacture evidence to help promote their absolute truthful experience. And so that could have happened with Meyer. We don't know. We don't know. We just know that the evidence he's provided isn't good enough, So that's the thing. And we also have junk science issues, it's really difficult for ufologists, because of junk science that gets in the way. Here's an example. In this particular, on this next slide here, if you go to the next slide, this is a SOHO satellite image, and this SOHO satellite image is illustrates an exact hold on, let me see what Morgan's saying here. I apologize, guys. This is I don't know. I'm saying to change the slide, but he's not changing it. Okay, all right. Anyway, he says he's on the right slide. I don't see it that way. That's fine. Anyway, I apologize. So SOHO, on this slide, if you notice, it's a blue slide. This blue slide is actually a close-up of an image captured by the Solar Observatory satellite that was looking at the sun. There's been a lot of these on the slides. As a matter of fact, here's another one. Now, what's interesting about these slides is they're not showing us gigantic spacecraft. They're not showing us ships on their way to the Earth. What they're showing us, in fact, is cosmic rays hitting a detector. They're classic images. If you go to the next slide, all right, it's the red SOHO satellite image slide, the second one, you'll see there's a set of 4 of them. And these 4 show different impacts by cosmic rays on the detector. They're typical splash patterns. And because this is a charge coupled device, a CCD detector, it typically makes the shapes that you see on the screen right now. These shapes are very classic shapes. There's overflow out of the bins because they're like little buckets filled with light, and they overflow and go to the next one. This is what happens. So, interestingly, as we move forward, we have this science to deal with, the real science of observing the sun, but then it gets distorted by pseudoscience, and that's a problem for us. Another one that I have a problem with is the Planet X folks. Now, in this image, in the next image of Nibiru and Planet X, all right, you can see that there's a bright dot near the sun in this image. Well, that actually isn't really a bright dot caused by a planet. That's actually a bright dot caused by a lens flare within the camera elements of the camera itself. And the way you can prove that is very simple. But when you talk to people that believe in Nibiru or Planet X, sometimes they don't want to listen. All you have to do when you take the picture is to rotate the camera. So what we want to consider here is that when you rotate the camera, you'll actually see that little dot in the image rotating with the camera. Now, I've said that to people. They've tried it and seen that they have moved Planet X around the sun. All right. So on this slide of Nibiru and Planet X, where you have the sun with that little lens flare up there, I've actually had someone tell me, and I just have to roll my eyes. Well, maybe because I rotated the camera, I'm actually influencing Planet X. Yes, it happened. And I mean, how do you argue with that when they have they're so invested in the belief? It's very hard. Now, here's the science. Planets can't be seen near the sun like this during the day, ever. All right? When the sun begins to set, you can actually see Venus a little farther away from the sun, and Mercury sometimes. During the day, you can't see Mercury near the sun, but Venus is far enough away you could actually see Venus if you know where to look. But it's a tiny, tiny dot in the sky, and you need a telescope to see it. So you'd have to dial in the right coordinates, all right? So now let's go to the next slide, which is the Comet Elenin slide. Comet Elenin was a convenient doomsday subject, okay? It came and went, though, and it evaporated when it went around the sun. And the doomsayers said, uh-oh, and they kind of moved on as if nothing happened, right? But you really should hold them to account and say, yeah, but something did happen. You said this was a doomsday comet, and when it didn't happen, rather than admit that your science was pseudoscience, you basically just moved on as if it never happened. And that's what we see all the time. So we're up against that, all right? And the other thing you also hear, and you all have heard this, all right, you always hear the people who talk about these doomsday comets and planets, you always hear them say, well, researchers have uncovered, independent study reveals, experts say, but you never know who they are. You never get to know who these people are. Well, in MUFON and with the scientific approach that we're taking now, you're going to know who they are. You know who they are. They're people like me. They're people like Chuck Maudlin. They're people like Steve Hudgens. They're people within MUFON who have the willingness to step forward and put our names on things and say, look, this is what it is. We have no problem with that, you know. So, but, you know, you have to say, well, you know, hey, newsflash for everybody, you know, some people don't believe in UFOs, you know, for all the reasons mentioned. They think they're nutcases, the tinfoil hats, or the movies have made them feel like Hollywood's invented the aliens. And, you know, we get all that. But so, again, what can we do to help people? We help them by using science. Now, if we go to the next slide, this newspaper slide, all right, this sort of illustrates that the media is our worst enemy. all right, because it began to discount the stories early on about the Roswell saucer. And to me, that's par for the course. That sort of set the tone for all time to come. So it's sort of an ingrained cultural manner in which we get treated. Now, through science like you're all gonna learn today, it's not far-fetched to think alien life exists, and everyone pretty much does. But the key is they can actually be here. And how could they be here? Well, many people say, well, they get here however they get here. But we actually have ways they can get here. Science can show ways in which they can actually get here. All right, there's a special drive called an Alcubierre drive, which we're going to talk about. And then there's propulsion concepts related to the theory of string theory, which we're going to see a little bit later as well. So we can use science to illustrate these two key realities, that ET life very likely exists. All right, we kind of know that one, intellectually. And also that ET life may very well have found us and could be visiting us. And we're going to illustrate those two realities pretty clearly. And on the next slide, this shows you all these, just a bunch of these planets. But we're going to actually go through how planets are found around other stars. What kind of techniques, what are the latest finds, what do they mean to us? Then we're also going to talk about something that's actually more important in a way, technological advance. Where are we on the cosmic scale of civilization? And where will we go? And when can we reach the horizon where we actually see some of these technologies that we might be able to leverage? It's all very important because knowing where we are helps us move forward. But the other thing that the talk will illustrate is that a supposition that I run on, I fully believe, and that is that the universe is predisposed to the creation of life. That's my belief. We can almost show that we will be able to show that pretty clearly. So, when you talk about exoplanets, let's talk about that for a minute. What is an exoplanet? It's a planet around another star. And they've been the fertile realm of science fiction writers for more than a century. And that stands to reason that science fiction, may one day become science fact, and we may actually live to see that there might be an inhabited planet before we're done here. But so understanding exoplanet research is actually quite critical. It changes how we view ourselves and the universe, and it will answer that question of whether we're really alone. And just so you all know, given this wonderful opportunity to talk to you all today, you have to understand that for me to do the research I've done and to have come to where I've come, I feel that I have stood on the shoulders of giants, and we all have. So it's to those giants that this talk is actually dedicated. All right. So we know that those who came before us help us get to where we are. So let's go on to the next slide. This is numbers. Now, this is one of the concepts that's hardest to get across, and because we have to use such big numbers to describe the universe, and that's the thing that people have such trouble with. I'll illustrate that in a minute. Now, Adam Frank, in his article, Cosmic Abodes of Life, he says that the universe is predisposed to allowing long-lasting stars, complex organic chemistry, and stable planetary orbits. Now, life as we know it requires exactly this scenario to come about. And that's something that we see in the universe. So that's a big plus right off the bat. But when we discuss the universe, we have to use numbers, big numbers, statistics for millions or even billions of stars. And now we know, believe it or not, there are more planets than stars in the universe. How about that? That is interesting. Now, humans can't visualize what a million of anything means. Now, our brains can handle about 1,000 objects, but it was never meant to harness such large values. After 1,000 somethings, our brains go all rubbery, and it comes out 998, 999, 1,000, and all the rest. That's how it is. So with exoplanets, we have to try and visualize numbers that are actually in the billions and beyond. And it's hard to visualize numbers. So we're going to try and stay away from throwing just numbers out. I like to use examples, and so we're going to use a number of examples. number of examples. Oh, yeah. So, let me illustrate the problem for you. Let's shrink the sun to a 5-foot diameter ball. Now, the sun is nearly 1,000,000 miles across, 860,000 miles across. So, if the sun was made 5 feet in diameter from almost 1,000,000 miles, the distance to the nearest star system at that scale, which would be the Alpha Centauri star system, that would still be 25,000 miles, or the circumference of the Earth. So you see, even with a model of the solar system where we take a 1,000,000-mile sun and we make it only 5 feet in diameter, we still have massive, massive numbers to deal with, and they still go astronomical on us. All right? So the numbers won't always make sense, but we'll try to do some examples to help along the way. But in order to understand, we need to go back 4.6 billion years ago to when we started. We need to use these big numbers anyway. So we're going to just jump back to the beginning because we have to understand how the beginning of our timeline works before we can understand where we're going in the universe. You'll see why as we move forward. So we have questions as a species. We look up to the sky and we say, we have questions. How did Earth generate life? Were we special? Could it happen elsewhere? Very simple questions. Well, let's see. So if you go to the next slide, if we look on this next slide here, this was the Earth and the predisposition to life. After the Earth formed from the solar nebula, then it was a collection of gas and dust and debris, basically, that mutually gravitationally came together. And of course, they start an orbital pattern. That's how it works. We can go through all that too, but only if there's in the Q&A later. Now it looked, Earth when it first formed looked quite a bit different, but it was normal at that point for an ordinary planet and an ordinary star. However, early when Earth formed, it looked, as in the next slide, it looked like this. This is what Earth was. Earth was a global magma ocean for a long, long time. And the reason was because every bombardment, everything that hit the Earth, caused that area of the planet to go molten again and become a giant sea of magma. And that's what we were. And this was called the era of bombardment. It lasted for, a long time, 1 billion years. And as material kept hitting the Earth and kept hitting the Earth, it kept re-melting that area. The net effect on the entire planet was that it went entirely molten. So about, I'd say 3.9 billion years ago or so, the meteorite and asteroid strikes began to wane. And at that point, as the Earth began to cool, things happened like, there was one more collision where the moon was formed, in fact. But then after that, as the Earth began to cool, we started to see crustal areas form. Right? So on the next slide, if you go to the next slide, you can actually see there were areas where there were still hot spots on the slide titled crust forms. And as this permanent crust would form, what would happen is in those hot spots, you would get volcanoes. So on the next slide, after crust forms, you can see a typical volcano. What's interesting about these is that volcanoes discharged immense amounts of gas. I mean, you can't really imagine the volume of discharge. But if you consider that when Mount St. Helens exploded in the late 80s, all right, or in the 80s, it discharged more greenhouse gases than human beings have ever generated in our history in that one explosion at the very beginning. So volcanoes are responsible for basically building the density of our original atmosphere. And that's what people have to understand. They're the consequence of the dynamic nature of planetary formation. And they're over hotspots, and they pop up, and next thing you know, we've got this gas and discharge coming out, and it happened all over the planet, again, once the crust formed. Now, we see volcanoes everywhere we look in the solar system. They're on many solar system planets. They're on Venus. They're here, of course. They're on the moon. They're on Mars. They're on Jupiter's moons. They're on Saturn's moons. They're omnipresent. So we have to assume that they occur in many other solar systems as well, and others around other star systems. And depending on the planet composition, they can expel many different gases. On the Earth, they send up CO2, water vapor, hydrogen sulfide, and other sulfurous compounds. On Jupiter, if we look at the next slide, okay, this little tiny moon of Jupiter, this is a real photo, by the way, of the moon Io circling Jupiter. Jupiter is massive. You can see it in this very pretty shot, but Io is only 2,300 miles across, but Jupiter's 87,000 miles across, right? Well, if we go to the next slide, you can actually see on the slide titled Jupiter's moon Io, you can actually see a volcano erupting on Io. But Io doesn't expel carbon dioxide, doesn't expel water vapor. It expels sulfur. It's a sulfurous and probably really stinky moon. So it's mostly sulfur compounds, which explains its yellowish, brownish, reddish colors, you see. Now, on the next slide, if we actually go to Saturn now, and we look at Enceladus, you can actually see that Enceladus has South Pole geysers. Look at all those. Now, these are what we would call volcanoes on Earth, but on Enceladus, they don't spew sulfur or hydrogen sulfide or anything. They actually spew ice and icy compounds. And there's a few hydrocarbons in there. Oh, hydrocarbons? Wait a minute. That's a building block of life, isn't it? We'll get there. We'll get there. So, next slide. It's a repeat of a previous slide, so don't panic, you didn't get lost. The Earth, being more massive, was able to retain heavier gases in its primordial atmosphere from all these volcanic eruptions. And the planets, all along, all through their life cycle, at one point or another, had atmosphere of some type. And most of our solar system planets did. The early Earth atmosphere, early one on Earth, was mostly carbon dioxide and H2O vapor with a lot of sulfurous and inert compounds. But the key thing was it was too hot. Water couldn't condense in that atmosphere. It couldn't rain. So the atmosphere remained for quite a while 90 times the density that it is today. Now, around 3.8 billion years ago, the Earth cooled enough that magic happened. It rained, and it rained hard. It rained for millions of years. I know, hard to believe. And being a weatherman back then would be easy. Yeah, still raining, so that would be easy. So what happened was the rain would run off the high areas and go and pool in the low areas. And those low areas, well, as you can guess, became oceans. Now, it's hard to believe that all that water formed this way from raining out of our atmosphere. But it's also impossible for you to understand, as it is for me, physically and intuitively, how an atmosphere 90 times denser could have held so much water vapor that it created these deep oceans that are miles deep and thousands of miles across. But it could, and it did. Now, one of the things that happened when volcanoes spewed out these gases were they spewed out a lot of carbon dioxide, and the carbon dioxide in that atmosphere actually dissolved into the ocean water. So that's similar to how CO2 today, carbon dioxide, is used to carbonate drinks and cause you that pain when it goes up your nose, right? Well, dissolved carbon dioxide formed carbonic acid in the water. Don't worry about it. But what it means is the carbon dioxide was absorbed by the seawater, and then the seawater cycled that into the rocks on the bottom of the ocean. And that's where we got our carbonate rocks, calcium carbonate and those other things. So seawater, because it could rain, you see, the seawater acted like a tremendous filter. It filtered all that carbon dioxide out of the atmosphere. That was great. Now, the technical term for that is a carbon sink. It just means it's a place for the carbon dioxide to get filtered, and it really worked great. Now, as an aside, we also know the oceans are salty. So how did that happen? Some of you may know, but when water runs over rock, there's two kinds of atoms that actually get dislodged very easily, sodium and chlorine. And when you get those two atoms dislodged, they all pool in the water, which became the oceans. And sodium, all right, it loses an electron very easily, and the chlorine needs an electron. So you end up getting sodium chloride because you get what's called, it's a bond, all right, between these two atoms, and you end up getting this bond, an ionic bond, and you end up having them bonded together, and you have sodium chloride, all right, and that's where we get our salty oceans. Now, you also know that our liquid inside of our bodies is also salty. It's the salt of the ocean. And what it is when we left the oceans as creatures, we finally started walking on land, we carried within an organ called the skin a whole vestigial ocean inside of us to maintain that salinity. Isn't that cool? So a consequence of the universe, in that sodium atoms can be dislodged so easily from landforms, is that we are salty creatures. I think that's really interesting. So we asked the question, how did life form, and how did complex molecules form in the ocean? Where did cells come from? And the bigger question is, if it happened here, could it happen elsewhere in the solar system and beyond? And it can be shown that Earth isn't unique. And alien life might very well be the consequence of existence on a similar planet in a similar place around a similar star. And as we'll see, not even necessarily a similar star. Now, on the next slide, titled the Miller-Urey Experiment, this experiment in 1952 by Stanley Miller and Harold Urey was meant to show if it was possible to create the building blocks of life experimentally by simulating the early atmosphere of the Earth. And in fact, they could. They put chemistry inside a flask, they added sparks and water, day-night cycles, and heating and cooling. And 1 week later, they discovered amino acids. And what that says to us is that the primordial atmosphere of the Earth was actually very, well, predisposed to creating amino acids, the building blocks of life. Now, that experiment was tucked away in a closet and looked at 50 years later. And 50 years later, they discovered that not only were those original few amino acids created, I'm trying to remember exactly how many they were. I think they only found like 5 or 6. But later on, 50 years later, when reanalyzed, they discovered that they had actually created 22, including 10 that they had not identified previously. So half a century later, that experiment still resulted in more data, which is really interesting. Now, if we look at the next slide now, so we're already getting the idea that the Earth is creating these building blocks of life. But you have to understand that the Earth was bombarded also by comets and meteorites. And comets show evidence of really complex carbon compounds on their surfaces. Now, we all call them, dirty snowballs, and that's kind of true. But there's some complex chemistry that occurs on a comet as well. And on the surface of the comet, we have these hydrocarbon-type compounds, which is really interesting. They're complex. So we got bombarded on Earth by probably millions of comets. And it's hard to understand that because you might have seen a comet once or twice in your life. But the universe has been around, our Earth, for 4.6 billion years ago it started. So we've been around for quite a while. So during that time, there was plenty of time for millions of comets to strike, and they did. And they brought to the Earth many complex carbon compounds. Now, on the next slide, many of the moons in the solar system are icy, and some of these planetary bodies show a hydrocarbon-rich environment. All right, and we're going to see this one here, Europa, shortly, because Europa has these deep fissures, and on the bottom of Europa's fissures are these hydrocarbon compounds, which is amazing that we see these. Now, if we go to the next slide and we look at the meteorites, all right, we have found meteorites that have had amino acids. In fact, one meteorite, which is what the picture in this slide, called the Murchison meteorite, brought 15 amino acids to the Earth. Now, that was just in modern day, within our lifespan, of, say 100 years. But over millions of years, how many amino acids did meteorites bring to the Earth to throw into our chemistry and start things churning? And the answer is a lot. So, together with meteorite amino acids, cometary from comets, carbon compounds, plus the amino acids generated by the Earth, we see that Earth, as a planet, can collect and manufacture the building blocks of life all by itself. And that's what we see. So this predisposition to the generation of organic compounds, that's a key concept, and that's something that we carry forward here in the talk. Now, let's take it a step forward. Carbon-based organic molecules led to amino acids. Amino acids collect into peptide chains. They string together to become proteins. Cell-like structures back then were probably more a collective of mutual organic collected cells that sort of profit from mutual processes. In other words, there was no real living cells. Now, here's where I say, magically, these eventually became cells. Well, I have to say that because no one in science can tell you how life actually began. But we can see all of the factors leading up to life, and then we have to stop because then there's that gap. And we know about that gap. We don't know what's in there, but we do know that life did begin. And we can assign any meaning to that we want, but it did begin at one point. Now, what's important is that this process that led in this organic soup to life was a natural process. And so on the next slide, life may very well be a consequence of the existence of a relatively normal star, relatively normal planet orbiting a relatively normal star in the universe. It's a statement of fact in my view. I believe that this is true, actually. So it's my hypothesis. Now, eventually, in the early Earth oceans, life began in earnest when these molecules began to replicate. And when they started replicating, they became, very, very, very prevalent. And on this next slide here, okay, you see our first life forms. Yep, about 3.8 billion years ago. Blue-green algae, green slime, but it is. I mean, green slime, cyanobacteria. These little guys were tremendously successful at survival. They've existed ever since then, all the way to present day. Now, these guys would actually remove the carbon dioxide that was remaining in the air that the oceans hadn't filtered out. And when they remove it, well, remember, it's a photosynthetic process. So what are they doing? They're taking in carbon dioxide and giving out, that's right, oxygen. Right? They're giving out oxygen. And so it's these little guys that populated our atmosphere with oxygen. How long did it take? Well, ever since 3.8 billion years ago, they've been pumping oxygen out. So you can see that they were going for billions of years. Now, what happens was when these algae would form, we see fossil evidence of these guys. This is how we know this, because we have on the next slide these physical forms called stromatolites. Well, a stromatolite is just the physical remains of a colony of blue-green algae. The way it would work is these were photosynthetic creatures. They wanted to reach for the light like plants do, but they would form a layer of slime over a rock, and then sand and dirt would come in and rest on top of that, and these guys under here would die and act like a cement, holding this sand to the lower level. And then they just keep putting another layer on top, another layer on top, another layer on top, and they would grow out like this. And as they grew out, they became these lettuce head-shaped, mushroom head-shaped forms, which are effectively rock, because they're just cementing sand and debris together. So, again, these little algae made our oxygen for us, and I think that's really fascinating. Now, if we go to the next slide, let's move now into the solar system. The solar system is a tremendous different number of planets. I mean, very different environments. If we move off the Earth for just a bit, go to the next slide, All right. Venus today is a snapshot of the Earth at one point in its past. It has a hot, thick atmosphere of CO2. It had a lot of water vapor, by the way. It has volcanoes. It has lava flows. But why is it different? How come it never had oceans? Because it doesn't have any. Why didn't that atmosphere thin as the Earth's did? You know the answer, I think, from the last things we talked about with our Earth's oceans. Venus had many volcanoes that spewed a lot of water vapor, just like Earth's. But it's closer to the sun's heat, and it never got a chance to cool down enough to allow condensation, that magic that happens. And with no rain, that meant that the atmosphere didn't thin. And no oceans from the rain meant that the CO2 atmosphere couldn't bind up with seawater and rocks. All right? And when that happened, Venus was sort of left with an atmosphere that's around 90 times denser than ours. Go figure, similar number. You can see it's a process that's sort of predisposed, see? So the lessons learned from Venus are that given a planet in the habitable zone around its star, that area where it's not too hot and not too cold from the star, that if liquid water can form, life is in all probability likely. That's the hypothesis. So this consequence of the formation of a planet in the right spot near its star is that you will have liquid water on its surface, an oxygen atmosphere, and potentially life. So Earth and Venus teach us plenty. And we find on Earth plenty of extreme forms of life. There's extreme, we call those extremophiles. There's extremophile life living in the deep ocean vents. If you recall, the Alvin submersible dove to the deep ocean rifts off the Juan de Fuca Canyon in the Pacific off Oregon, and they discovered black smoking chimneys that are rich in minerals. They also discovered oases of life, strange life forms. They found giant tube worms 5 feet long, and these things actually had hemoglobin in their systems. Yet, there was no photosynthesis going on. It was all chemical synthesis, chemosynthesis. So, once we saw those, we realized, wow, in the deep Antarctic, or in hot springs, or in asphalt lakes, you could actually certainly find extreme life. And we did, and life thrives there in many ways. Now, scientists believe that the starting points for life probably occurred elsewhere as well, even in our solar system. Let's go to the next slide and look at Mars. As we know, Mars used to be a very wet planet. And over time, that water was lost to space and into the ground rocks. Yet under the surface of Mars are known water ice deposits, big water ice deposits, frozen, of course. The Phoenix lander, which landed sort of in the northern regions on Mars, as it landed, it blew off sand and dirt from the ground, and it literally is sitting on ice, solid water ice. It's a tremendous tremendously hard surface. So the fact that the probe wasn't damaged landing on that hard surface was amazing. But if you look on Mars, there's evidence of tremendous water outflow. This image actually shows you Valles Marineris right across the center. It looks like a giant slice taken in Mars. Well, that's a massive rift valley, but leading into it are all kinds of water outflow channels. And there's plenty of positive evidence, which is almost taken as fact now by the rover teams, that there are massive lakes found on Mars that, of course, are dry now. But you see the terraced lakeshore. You actually see that terraced lakeshore from a receding lake over time. And that's been found by one of the rovers, like Opportunity, for instance. Amazing stuff. Mars also has shown us evidence of methane. Now, methane, in the Martian summer of 2003, indicated that maybe there was some volcanic activity going on. Except, Mars is volcanically dead. So what's the other source for methane? Bacteria. Bacteria. They give off methane as waste. So, it's possible that maybe the methane was released from permafrost under Mars as Mars warmed, potentially. Or it's possible that the methane plume that we're seeing is actually microbes that exist today that bloom like algae does in the ocean, and that bloom when Mars has its warmer months. Now, on Earth, methane lasts about 14 years. Then it oxidizes and becomes CO2 and water vapor and stuff. On Mars, methane doesn't last long because it's got a lot of ultraviolet radiation that makes it down near the surface and can actually break the methane apart in as little as a year. What does that mean? This means that if we see methane, it means it's a recent find. It's recently generated. Key point. So, if we see seasonal methane, it could be an indication that we've actually found our first extraterrestrial life, and it might be on Mars. Now, the observations of the methane have not yet been reproduced, and that's been 2003, so they're still trying. Maybe it's that we're not looking for the right thing or in the right place. But we take some lessons. Even outside of the habitable zone, which Mars is just outside the habitable zone, toward the colder end, Mars for a time was able to sustain water and perhaps, even to this day, microbial life, tenaciously hanging on below ground. Really, really amazing to think about that. On the next slide, this is the Jupiter system slide. We have many mysteries at Jupiter. This is a little rendering I did of Io with Jupiter. Io is that moon I told you about that has the sulfur volcanoes. I wanted you to just get a little bit of picture of Io in color, so you can kind of see its coloring. It's yellowish red. Well, if we go to the next slide, let's go to the moon Europa. If you look at this cutaway, the blue part you see is actually the ocean that we think is there. And the outer crust is a thick, frigid ice cap, basically covering an ocean. Now, we think, based on what we see on Europa, on the surface, where we see all these fractured fissures with this carbon compound material deep in those fissures, we think that Europa's oceans might actually be an oven that's creating, the building blocks of life. This is something that we want to consider as a target, this place, as a target for future exploration, wouldn't you think? I would have to say so. Now, as I said, on the Earth, in the deep ocean vents, okay, we have 700-degree water laced with volcanic gases, and they support chemosynthetic life of all kinds. And the life found there in 1977, as I said, was outlandish at the time. Those tube worms, giant clams. But it's a symbiotic relationship with hydrogen sulfide eating bacteria. Something we never thought possible. But because of that deep ocean rift finding, we could see Europa now at Jupiter as being a possible candidate for similar type life. Because we see the exotic right here on our own planet. And we never knew it until 1977. Interesting. Now, if we look closer at the surface of Europa, we actually see it's a jumbled mass of these icy massives that they actually move around against each other and open. And those freckles, if you look on the next slide, all right, these splotches you see on the surface of Europa, in the freckles, you actually see these brown splotches. This is a photo. This isn't a rendering. And you see these brown splotches, and what these are areas where organic material is being pushed to the surface through cracks in the ice. Wow. So we think this is a place for future probes. Drill a hole, go down in the ocean, see what's there. Now, on the next slide, we talked about Enceladus at Saturn. Let's go to that moon again. Now, this has a strangely similar composition to Europa. Okay, but it spouts, like I said, these massive geysers of icy material from its interior, and it's around the South Pole. The funny thing is, the water temperature inside the surface, below the surface, is a relatively comfortable 0 degrees Celsius, 32 degrees Fahrenheit. It's warmed by geothermal processes. So the thing that's funny about this is Enceladus is only 314 miles across. It's tiny, yet it's still doing what it's been doing from formation 4.5 billion years ago. It's spewing hydrocarbon-rich material onto its surface, which is just incredible. Now, at that South Pole, they found water vapor, CO2, nitrogen, and these carbon-based molecules. Now, they also think, scientists think, that Enceladus could also be an oven producing building blocks, and that should also be a pit stop for explorers someday. Also at Saturn, on the next slide, we see Saturn and Titan. And Titan is almost a planet-sized moon of Saturn. And it's really been a subject of scientific study for many years. If you go to the next slide, here's a radar view looking down. It shows a methane lake, liquid methane. Want to go to the beach? I didn't think so. But it's so frigidly cold that methane is liquid on the surface. And if we take a look at the next slide, in these renderings here, you see what it might look like if we got down to the surface. You can actually see rocks covered with these methane precipitates, and then you actually see the liquid methane lake. And if we go with the next slide, you can actually see the actual beachhead, the actual beach, with some of these strange forms that we would find there. Now, when we go to Titan, we went with the Huygens probe as part of the Cassini mission. And Cassini launched this probe, and it successfully landed on Titan. And if you go to the next slide, you can actually see the real image sent from Titan. This is what the surface of Titan actually looks like where they landed. Now, it has a dense nitrogen atmosphere, Titan does, and it's also mixed with these complex hydrocarbons. Here we go again, the primordial soup from which life, under the right conditions, can come about. For our kind of life, Titan is too cold. And Titan has lots of water ice, but it's rock hard under the surface. It's kept bound up. So by now you can kind of see the picture that's taking place. There's the potential for the building blocks of life, and perhaps life itself, right here within our own solar system in a variety of what we thought were incredibly inhospitable places. And people need to understand this so they can see that the road to life appears almost everywhere we look. Now, we go to the next slide, please. Understanding how we came about allows us to look for other worlds, and that's one of the things that we want to do. You know, we want to look for other worlds. Now, right now, we're at nearly 1,000 planets that we found around other stars, and we know that there are more planets and stars, as I have said. So that gives you an idea of just how many more there are, because we know there's trillions upon trillions upon trillions of stars. So many of these stars will have planets that are in the habitable zone. That is, the not too warm, not too cold location that we talked about before. Now, in our solar system, Venus is just inside, just outside the inner edge, and Mars is just outside the outer edge. So you kind of see, and Earth is sort of in the middle, not really quite, but almost. And we've also discovered out there that many other star systems have more than one planet. And some of these are super Earths. And if we go to the next slide, okay, a super Earth is a planet that has less than 10 times the Earth's mass. That's going to be pretty interesting. If you're on a planet that's 10 times the Earth's mass, you'll weigh 10 times as much. That's not good, I know, I'm sure. But in this image, we actually see one super Earth that we actually found called Gliese 581d. Very attractive name, I know. They're working on it. But 581d is going to be a hot topic for years to come. The temperature on this planet is between 0 and 40 degrees Celsius. So in other words, it's not bad. It is 6 times the Earth's mass, and it has several other planets in the solar system with it. But the star it circles is nothing like our sun. The star it circles is actually called a red dwarf. It's a star that's only about a third the size of the sun, so the planets are all, and this planet's much closer to the sun, its sun, to actually feel those temperatures like we feel here. And it's actually a red star, kind of like sunset even at noon. So it's a really interesting place. Now, when we look for planets around other stars, we mostly find big giant planets, okay? But finding the smaller, rocky, terrestrial planets like ours, they're harder to identify, but it's becoming more possible. And here's an example with 581d of just exactly how we do that. But how do we find them? Let's go look. Let's start with the next slide. Now, stars are really far away, and planet hunters have been at it for a long time, and the task is monumental. And let's look at an example. Rather than use numbers, let's look at an example. I talked about that nearest star, Alpha Centauri, 4.3 light years away. All right. A light year is the distance light travels in a year. It's about 6 trillion miles. It's also, if you were to aim a flashlight horizontally along the Earth and you could reflect it with a mirror all the way around the Earth until it hits you in the back of the head, it would hit you in the back of the head 7 times per second. That's how fast the light beam can go around the Earth, 7 times in a second. So that's pretty fast. Now, at that speed, you know, it's still a long way to Alpha Centauri. If we were to send a spaceship there, it would take us over 20,000 years with our current technology. All right, so it's about 25 trillion miles away. There's the numbers for you. However, let's look at an analogy. Alpha Centauri is like our sun. It's only slightly larger. Our sun's 864,000 miles across, and Alpha Centauri's main star, there's 3 in that system. We won't even go into that yet. But Alpha Centauri's main star is 1.2 million miles. So here's, you know, Sun, here's Alpha Centauri, a little bit bigger. How far away would we have to take an ordinary quarter, an ordinary coin, the quarter, and put it from us so that the size of that quarter in diameter in our telescope would be the same size as the disk of Alpha Centauri would appear in our telescope? How far would that quarter have to go for us to see the diameter of that quarter, the same diameter as Alpha Centauri's disk is seen in the telescope? That distance is 713 miles. So that means, in your mind, you're already thinking, wow, you mean I can get a telescope and look at a quarter 713 miles away and see the disk shape of the quarter? The answer is not very easily, even for the nearest stars. Yet planet hunters are effectively finding planets around the star that are the equivalent of seeing not just the quarter's disk, but the date on the quarter and only fractions of those numbers on that date at that distance. Think about that. That means that we have some pretty good techniques already on tap that we've been able to use. So one of the techniques, let's go on to these. One of the techniques is astrometry, and on this slide, this has a video on it. So this will, you know, once this comes up, when a planet goes around a star, this is one of the oldest methods for searching for exoplanets. You actually measure the star's position over time. You don't directly see the planet at all. But what happens is the planet might be massive, and as the star and the planet circle each other, you actually see that the star moves a little. It wobbles. It goes back and forth because the star and the planet are actually orbiting around a common center. That's called a barycenter. Same kind of thing if you take a little child and you start swinging them around. You have to lean back, don't you? Because if you don't lean back when you swing around, what's going to happen? You're going to fall over. You're going to be pulled, and that's a problem. So this is, you know, this is an illustration of that. Stars do that. They wobble in their motion, and that wobble can indicate that there's an unseen companion. Now, most hits with this technique in the 50s and 60s were erroneous. Like it's extremely hard to measure a star's position accurately with ground-based telescopes. The Hubble in 2002 correctly found the planet using this method, and it works really only for nearby stars, because the farther they get away, you can just imagine it's much, much harder to see that effect of this tiny, tiny wobble. The star doesn't move so much, in fact, that it moves way out, back and forth. It only moves a slight amount within its own mass. I mean, within its own, you know, space that it takes up. So it's really, really hard to detect that. Now, I worked in an observatory, actually, where we detected the motion of nearby stars, or the distance to nearby stars, by looking at the motion like parallax. We would actually, it's like if you hold your finger out like this in front of you, and you close one eye, and you close the other eye, it looks like your finger is moving against the background of the wall behind you. Well, imagine if your finger was a star that's close, and the background wall was a bunch of stars farther away. We measured at one end of the Earth's orbit. We would measure the position of the star against the background stars, and then at the other end of the Earth's orbit, we would measure the position against the background stars again. Yeah, there's the video. And that gave us the distance to the nearby stars. That's called parallax. That only works for nearby stars. In a similar way, checking the wobble of a star only really works for the nearby guys. Now, if we go to the next video, this one is the radial velocity or Doppler effect. What happens here is, along with that wobble, we can't actually see the wobble because the star is too far away. We can see a change in the color of the light. Now, that's interesting. As objects move toward us in space, their light gets blue shifted toward the blue end of the spectrum. Remember, the spectrum goes red, orange, yellow, green, blue, indigo, violet. So that, and we call it that Roy G. Biv. That's how we learned it, right? Well, if a planet, or a star rather, is coming toward you, it's going to be shifted toward the blue color of the spectrum. If it's going away from you, it's called redshift, then you would actually see the color change toward the red, as illustrated. Now, that was the wrong video, Morgan. That's transit. But the Doppler effect can be seen when you can't see the wobble of the star. All right. So when you see the actual color change, that's called radial velocity. You're seeing a component of the star's motion coming towards you, and some of it going away from you, and it changes the color of the light. That indicates unseen companions around that star. And we use this a lot, in fact, to corroborate data showing planets in other ways. So we use all these techniques against each other to second guess and prove. So the amount of the red shift or the blue shift can kind of provide a minimum size the planet might be, or mass. And the good thing is that this method, again, is relatively independent of the distance. So whereas you can't see the wobble, you can see this Doppler effect. Believe it or not, of the 1,000 planets, 456 have been found this way so far. All right? And now, going to the last video, when we look for a planet using the various methods, one way that actually works very well is one called a transit. Believe it or not, for all the many planets circling stars out there, some of them actually do eclipse their star, as seen from Earth. That means that they actually go between their star and us. And when they do that, all right, as seen in the video, you actually see a reduction in the amount of starlight that reaches you. As the planet first starts to go in front of the star, the light begins to dim, and you actually see the light, it's called a light curve. The light actually starts to dim, so you see the light dimming like this, and then as the planet comes back out and leaves that edge of the star and heads back out, you actually see this little tiny well created in the light curve. The width of that well can tell us how fast the planet is orbiting. The depth of that well can tell us something about the size of the planet. There's so many things we can get from the light curves. And one of the things I did when I was getting my degree in astronomy is we did all kinds of things with light curves. It's called photometry, where you study the amount of light coming in, and then you take out noise and figure out just what's going on a star based on the light curves you see. Really, really workable science, real good science. So the interesting thing here is that when the planet is first coming onto the star's surface, when it first starts to come in, you can actually see the atmosphere of the planet first. And when you see the atmosphere of the planet, then you can actually start looking for some of the chemical signatures of life. Now, it'll happen. We will find a planet in a habitable zone, and we will see oxygen in that atmosphere, because that's the key. When we see oxygen in the atmosphere, we know that the planet probably has life. The reason is because the planet reaches something called disequilibrium. Oxygen on planet Earth doesn't want to be here. It actually wants to get bound up in rocks, and it does every day. It wants to get bound up and made into other compounds all the time, and it wants to every day. But that equilibrium that Earth would reach if we didn't have plants would be that the oxygen would be gone in a fairly short amount of time, maybe 1 million years. However, because we have plants, we're generating an overabundance of a particular molecule on Earth that doesn't want to be there naturally. And that's the O2, the diatomic oxygen, or the oxygen molecule. And this disequilibrium is what we look for in exoplanets. We see that, it means that life is creating that oxygen. And that's a pretty certain thing. So, that all said, when we find life on another planet like that, you know, who do you think will be the first Earthlings to visit such a planet? Scientists? Engineers? Astronauts? No. Real estate agents. Hey, they're going to sell you a place right there next to that really cool supervolcano. You watch. Now, the downside of the transit technique is that it does produce a high rate of false data. But not to worry. It's really cool. It works well enough. Moving on to the next slide. Okay. There's a few other techniques too. You know, there's sometimes we see disks of dust around a star that can tell us a few things, and we can see a star's atmosphere seems to have some kind of molecules in it that the star can't have. This next slide actually shows us something about the stars now. All right, and when we look, you'll see exactly this is called the Hertzsprung-Russell diagram, and the Hertzsprung-Russell diagram, you see in the center it says sun with an arrow pointing to the middle. If you look in the center, you see that kind of long sloping line from the upper left, goes to the middle, and then kind of goes down to the bottom where it turns red. These are all the normal stars. What are normal stars? Normal stars are actually called dwarfs, but they're massive. I mean, you know that. I mean, we've talked about that. You know, the sun is almost 1 million miles across. That's no dwarf to me. But in the universe, they're called dwarfs. And the reason is because they just do ordinary burning of hydrogen to create helium. It's their normal technique for doing hydrogen fusion. So the interesting thing about this is that on this diagram, you'll see along the bottom these letters. Stars are designated with what's called a spectral type, okay? OBAF, as you see, all the way to M. We are a G-type star. And within the ranking of G, you'll actually see that there's 10 different levels. So you have a G0 all the way to a G9. All right, we're a G2. Now, the left side talks about luminosity, or the brightness of the star. The ones in the upper left, the bluish ones and the white ones, those are the guys to watch out for, because those are the guys that all tend to go off in a massive supernova. And what's interesting about supernovas is, if we go to the next slide, supernovas are where we get this. Everything that makes you, everything that makes Earth, and except for you know, some of the actinide and lanthanide series down the bottom, okay, the periodic table, the elements for the periodic table come from the cores of stars. Carl Sagan used to have a show called Cosmos. I grew up watching Cosmos as a kid. I really enjoyed it, and he used to say, "We are made of star stuff," and he was absolutely right, because that's exactly what we are. We are star stuff, and every element there was made in the core of a star, and so everything that makes you up was once made out there in the universe. It's hard to think that through sometimes. Now, if we go to the next slide, okay, this next slide, after we look at these stellar types, okay, we talked about these different types. We talked briefly about those really red stars, the M stars, down in that lower right part of the diagram. We've also discovered something fascinating, and that is that these M stars are the most common star in the entire universe. Not only that, there are so many of them that have planets that they've changed this whole planetary exoplanet research arena tremendously in the last few years. Not only that, you can't find any one of them in the sky with your eye. In fact, in a telescope, they're hard to see. They're so small and so typically faint that they're actually invisible. They're not invisible, you know, if you were there, they'd be like you see in this image, you know, K1V, M2V binary star system thing, all right? This image I have on the slide. This is what they would actually look like if you were there. They'd be very bright. But it's fascinating to think that these stars, which harbor the most planets in the entire universe, are actually invisible even if they're relatively near each other. And we think that's interesting. Now, if you go on to the next slide, we're going to look at a couple of interesting exoplanets here. This one, HR 8799, another great name, right? Really attractive name. It was found by direct imaging with the Gemini telescope in Hawaii. Now, That's on Mauna Kea at the observatory there. Now, I talked to Pete Michaud, who is the Gemini Observatory guy, the director, and he's also running this program, and he provided this image for me for this talk, so we have him to thank for this. This was found 129 of those light years away, and the significance is it was the first image of an entire solar system ever taken, and you can actually see all the separate planets there. And by the way, when I say separate planets, that black disk in the middle is just a what's called an occulting disk, which actually blocks out the glare of the stars so that the instrument could detect the very, very faint signatures of those planets like that in the image. Now, outside that disk, it's actually the closest planet is the distance of Neptune, the closest one to that disk. All right, so you can imagine within that disk, lost within that glare, could be an entire inner solar system of planets like Mercury, Venus, Earth, Mars. So really interesting. If we go to the next slide, I mentioned disks of dust around the star really briefly. This star, Fomalhaut, okay, is actually the brightest star in the constellation of Pisces Austrinus. Don't worry about that. But it's a pretty hot star. It's 25 light years away. And the significance of this little inset box down here, if you notice, you see down to the lower right, it says 2004, 2006. Well, look at that. That little bright spot moved that distance. That's a planet, folks. That's a planet found by direct imaging of a dust ring around the star. The black artifacts you see in the center of this image are just, you know, areas where there was some missing data, and of course the occulting disk, which is the coronagraph mask that's in the center that we talked about there a minute ago. So that's a fascinating find. Now, we already talked about the next slide a little bit. This is another video, and it's Gliese 581d, but there's actually B, C, D, and E in this solar system. And in this video, as we approach, you know, we go past the star, and we move on through one of the big, you know, the giants, gas giants, and then we come through now to what looks like a possible Earth. Now, the interesting thing is it's 1.6 times the mass of the Earth, as we mentioned earlier when we talked about the comparison showing the two side by side. And they're only renderings, of course. The Earth, we know what it looks like, of course, but 581d we don't. But it's one of the smallest planets found so far, as close to the Earth as possible, and it's sort of in the habitable zone as we talked, so it could have liquid water, and that means it could have life. So, we're going to move on. I want to get to a little bit of the galactic technology tree, so if you can go to the next slide. You know, this, the galactic tech tree slide. All right. You have to understand that the universe may be full of civilizations, and we want to know what challenges await a civilization in their quest, you know, to become a spacefaring race. You know, will they choose to you know, explore the universe, or will they dig in at home on their world? We don't know. You know, and we all face self-annihilation, disease, natural disaster, death from another civilization. One thing that's in common, if they survive long enough, they are going to face the need to leave their planet. All right? And and again, the correct slide, to be honest, galactic tech tree. It's the one after the slide marked HD 189, etc. There you go. Sorry, I'm looking at two different sites and monitoring their presentations as well, so I apologize for that. So one thing, like I said, we have in common, we all must become a spacefaring race eventually if we're going to exist and continue. And as for us, we've only just appeared on the cosmic stage, folks. As hominids, we've been here for 4.4 million years. That's 1/3125th of the age of the universe. I calculated that just now in my head. No, I did not, actually. I lied. I did not. Now, as Homo sapiens, we've only been here about 160,000 years, and we appeared in Africa. Now, our written history is 30,000 years old. You know, we are young, cosmically, in other words. Now, understanding that age scale of our planet and our history is really interesting. And when I do this presentation live, I just did this in Phoenix, I unroll a most unlikely metaphor to help me explain the history of the Earth. I take a roll of toilet paper out, and on the roll of toilet paper I have put all these historical timelines. Yes, I unrolled the whole thing, drew on the toilet paper, rolled it all the way back up. Okay, I'm a nut. I apologize, but it's effective. And what I do is I unroll from the very beginning. It's 4.6 billion years in the past, and that 4.6 billion years is the start of the Earth. And as we go forward, we start unrolling these sheets. There's 350 sheets, by the way. At 350th sheet, it's the 4.6 billion year mark where Earth's form, its history begins. The moon forms 342 sheets in at 4.5 billion years. At 259 sheets in, you notice we've gone through 100, about 100 sheets of toilet paper before the first bacterial life shows up. All right, and then before even the first continent formed, which was Rodinia, okay, we were 106 sheets from present day. All right, and the Cambrian period, the 544 million years ago, was 41 sheets from present day away out of 350. You see, it's a long timeline, and that's the first, shelled creatures. So from 259 sheets from the present day to 41 sheets, we've had oxygen buildup from bacteria through all those years, the cyanobacteria I told you about. Now, moving forward, the first insects didn't appear until 30 sheets from present day of toilet paper. The Pangea was 21 sheets from today. The Triassic period was 19 sheets. Jurassic period was 15 sheets away. All right, and dinosaurs, dinosaurs actually died only about 4.9 sheets from the present day out of 350 sheets. Now that's, by the way, that's 116 feet of toilet paper. Yeah, I measured. Okay, I measured. Give me a break. I just had to know the number. It was kind of cool to know that. So 5 sheets away basically was when dinosaurs were extinct. Now, if we keep going just a little bit further, what's interesting is on that last sheet, which is where we are, all right, 3/4 of the sheet, 3/4 of a toilet paper sheet in out of our 350, that's where the Red Sea opened up. That was 10 million years ago. And only 1/3 of a sheet in did the first hominids show up, Australopithecus and Lucy. We're only on 1/3 of a sheet out of 116 feet. That's just, just over a centimeter, and just a couple centimeters out. 1 centimeter from the end of the sheet was Homo erectus 1.3 million years ago. And now to put it right down to the present day, everything we know from the Sumerians on to the present day fits inside of a line that we can't even draw with any known existing writing implement. That's a line that's only 0.001 millimeters in width. Now, that's all that we've ever known. So that's our existence in the universe. 0.001 millimeters, all right, out of a 350 sheet existence of the Earth, which was 4.6 billion years ago when it started. And the universe has been here for 14 billion years. So, what's that mean? It means that, well, first of all, the next time you see someone toilet paper your neighbor's house, you can look up and say, look, Earth's history all over the tree, and the dog is tearing up us on that last sheet down there on the lawn. But the other thing that's more important, actually, is to say, can you imagine an alien race that developed 3/4 of a sheet back from us? Because we've found planets that are only now just in formation, and we've also found planets that have survived the death of their star. So it's a sliding window. It's been going on. It's going birth and death, all throughout the length of the universe's lifetime. So that all said, it's really important to understand that life could certainly exist. And as we develop higher technologies, physics indicates ways for us to travel faster and use ways to actually avoid the light speed limit we all often hear about. Because when we talk about light speed, one of the things that we have to consider is it's a limit in our universe. But physics is just over the horizon. We can see physics that indicates we don't necessarily need to use our current constraints, our current universe. We can actually kind of get out of our current universe a little bit and actually use different physics techniques to travel. The Alcubierre drive is one of those. It is the quintessential warp drive. And it's actually, physics dictates, in fact, that it's a plausible possibility. Now that means we can actually get to the nearest stars in 2 weeks, Alpha Centauri. And if we really crank up the drive, we could do it in 2 days. So there's that possibility. And then even a little bit farther over that horizon, we actually see a technology within some of the string theory principles that literally, and I know this is like going to sound like just pure speculative science fiction, and it's somewhat speculative, but it's not science fiction. This is based in string theory physics and some other astrophysics. It's possible that we could actually get to any place in the universe in seconds. Yeah, I know, it sounds crazy, but the fact is, if we can leave the constraint of our existing universe and get off our space we live in, we can punch in anywhere else we want to go. And that's part of the whole theory. When we have another, if there's another talk sometime down the line, I can actually go into just that and spend time illustrating that in a way that actually makes sense, with examples and not big numbers, ways to actually make sense of it. So as we progress, we could really likely see the eventuality of traveling to the stars. And one of the things is we have to understand, like I said, how life began here so that we can look for it elsewhere. And then when we find it elsewhere, it kind of gives us an idea what to expect. And I've always said that when we first meet an alien race, it'll be in deep space, because we will send a probe out and they will have seen us coming and they will come out to meet us before they let us get to their planet. And we should do the same. All right. So anyway, I'm just going to close because I realize I'm, with everything going on, it's a kind of a crush of time here. I apologize. But I will just close with this little poem that I wrote, which kind of just says, it's 4 lines. This says it for me. The myriad stars above at night, their millions-year-old wandering light. With every starry point I see, someone else looking back at me. Thanks, guys. And I realized it was really fast.
Hey, thank you very much. That was excellent. We had some sound challenges here, but we all enjoyed watching your presentation. It was enormous. My head is also doing a wobble, very much like that star that you showed, and I'm never going to look at toilet paper the same way.
That's right.
That's right. I want you to know that I'm in awe of that very fact alone.
Well, next time you go to the bathroom, Rich, okay,
yes.
Just say to yourself, well, there goes the Jurassic.
Jurassic, yeah, that's very true.
I wasn't going to go there.
No, I just thought you were talking about maybe Uranus again. But anyway.
He said it, folks. I didn't.
I did.
Every time I switch the screens over here, that's the faces and things in the rack.
By the way, Morgan, does this have a bleep factor that you can look at for censoring us? I don't know.
Probably not.
Anyway.
You're doomed.
Anyway, I want to thank all of the groups who have been sitting for hours as we've gone through trying to deal with the technology stuff and also to get this thing going. I really appreciate everybody's time on this Saturday. And especially Mark, thank you very much for pulling it together.
I also appreciate your time with Morgan and you, Rich, trying to work it all together. And for everyone to understand that this process that Morgan is sort of championing here is actually one of the future better ways that we're going to actually be able to carry out meetings for multi-state and to do presentations. And it's going to get less limiting, as we move forward, because if the source, if I, for instance, have a far better machine with better video capabilities, we're going to get some better quality stuff. So.
Yep. Well, again, thank you. And thank all the people down in Florida for joining in, too. And Morgan, thank you again for inviting us or attaching to us, so we get to share that same experience. So thank you.
Yeah, can you guys hear me okay?
Yeah.
Yes.
Good, yeah, no, I'm glad to be here, and yeah, it was a little struggle in the beginning, but we actually have a Mac and a PC working together to get this to work correctly. And yeah, go figure. The universe is imploding as we speak, but it's working, and I have it all recorded. I was controlling the screens of what was being viewed. A little bit of issues with the animations, trying to get them up in time because they don't have a thing for that. But everything is going to be pre-recorded. So when it's over, there's going to be a YouTube link where you'll be able to watch the whole thing again if you missed it. So yeah, the technology is growing, and as far as I know, there were a lot of people online watching. So that's another encouraging sign too. So. We'll see what those numbers are in a few weeks as they climb. So,
Yeah.
Rich, do we have time for a few questions
From
the audience?
my group. The audience, okay with questions? Would you like to
talk to Mark? And maybe it can go into UFOs and everything else too. So
Yep. I mean, you got the chief photo and video analyst from MUFON right here. Are there any questions about that, or
you guys
some of the things that he's got going on? Anybody in the group here?
Anything?
There's, you're going to have to come over here to have a comment.
Wait.
Has to do with self-organizing systems.
I just wanted to say that I think Mark is brilliant. He's not nerdy. But
You can have her come up to the screen if you want.
No, never mind. I don't know.
She doesn't want to do that, but
okay.
She just wants to say that Mark is brilliant, and she definitely appreciated what he had to offer.
Oh, well, thank you very much.
Anybody else have a question?
I heard not nerdy, and I thought that was a good one.
Yeah, he's not nerdy.
Wait, I can do that. Wait, here we go.
Oh, there he is. There he is.
Exactly.
That's better.
She rescinds her comment.
No
Thank
other.
you for that. That was very nice.
Yes. Hold on. One other question here.
Everybody's afraid of not doing it. It is.
14-year-old started recognizing the chemical chart.
Oh, yeah.
Starting to study
it.
We have a number of grandchildren who joined in on this session. I personally had 5, and we have another grandchild that's here as well. And despite your nerdiness, they appreciated what you did and what you said, and they liked your metaphors that you used all the way through the presentation.
Oh, they're going to love toilet paper at home, too, and their parents are going to hate me.
I am definitely going to like it.
All right, well, that was a thank you from it. So we don't have any other any questions. Morgan, do you have questions there?
Well, I don't know. Not a few. I guess most of the guys are pretty satisfied. They seem to have. I guess they were pretty fulfilled. I think he answered most of the questions. But as far as your role, Mark, in MUFON as the chief photo video analyst, what do you see for the future within MUFON and analyzing? And then also another question more towards UFOs. There was a comment from one of our members here in Florida that says, "Well, I've been listening to these conversations for." For 30 plus years, and it's like everything is repeating itself as far as the arguments, the discussions. What is going to happen that's going to change things in this field as far as its conversation? What are we going to start doing to make things different?
Well, Morgan, that's a really good question, and you know what? I hope everybody can hear me, because here's what's going on. Now, I became, I was in MUFON in 1971. That's when I started. All right, I was 11 years old, and MUFON back then was Walt Andrus had file folders on his desk with pieces of paper that he would send out to people to look at interesting cases, and very occasionally you might actually get a long-distance phone call. Wow. Okay, but now we have a lot of technology at our disposal, and we also have scientists at our disposal. MUFON, in spite of what may or may not have happened within MUFON in the last number of years, or this last decade or so, MUFON's actually steadily progressed toward a more scientific approach that actually is unparalleled in other organizations right now. And one of the things that we're doing is, and Morgan's involved with this, as is Rich. We have a system that we're going to talk to everybody about. It should be a presentation of its own. We are creating detection systems that are going to be able to detect UFOs. And one of the problems we have as a photo analyst and as a ufologist is that when we look at photos, we usually see one fuzzy photo or one video taken with an iPhone, and it's usually moving like this. Oh, look at that. And, we're not getting a whole lot of information from that. So what we're going to do is we're actually going to create these systems that are going to have multiple units, multiple instruments on board. Not just visual, but things that will detect certain types of radiation and other things. We've already got a number of these working already. And they're going to communicate with each other, and they're also going to take this data and send it to us. And we're going to actually get to look at sightings and possible UFO sightings from a variety of points of view of different instruments, all looking at the same sighting together. And we will have the prototype up and running probably within 6 to 10 months. I think we have software programmers on board. We have former government scientists on board, actually, who worked on very large systems, including putting probes around the moon, on Mars. And they're all part of this. This is not just ufologists getting together in a garage and saying, let's make something. This is a science team that's established across the country. And, I put that team together because this is needed in ufology, okay? And I could care less, about people that want to come and be critical and say, well, that's not going to work, that's not going to work, or whatever. I understand that. You see, I'm pushing past all the criticisms so that we can get to a final result. And then the final result is going to be that MUFON is very likely going to be a major player in the distribution, maintenance, and operation of these nodes that we're creating. And we have them for land and we have them for sea. We've designed one for the ocean, and the one in the ocean is going to be looking down and looking for USOs. So that's where we're going as we move forward. Rich is not, he's muted. I can't hear him. I can't hear you, Rich. You're muted. Oh.
I'll repeat it again.
Oh, okay. You're funny.
Hang on, we got a question here.
Sure.
Are you hopeful of being able to find some information about the domes that were sighted off Catalina, which apparently are some sort of artificial structures underneath there? Do you think that those are valid as artificial structures?
Well, interesting you mentioned Catalina. You're talking about by chance, the Santa Catalina channel?
Yes, correct.
Yeah, that's one of our deployment locations for our system, actually.
Excellent. Yes, yes.
Yep. We have a number of them. The Santa Catalina channel is one of them. We're with you. We're with you.
Yay.
Grandpa, I have a question.
We're with you.
Thank you.
We know that there can be life out there, but can there be like intelligent life more?
Yeah, that's what I said. For sure.
Yeah. Like.
Well, that's okay. Actually, I would like to address that. Go ahead. Ask your question.
Go ahead, Brian.
Brian, my 14-year-old grandson's got a question. Go ahead, Brian. Say it again.
Is suffering a bandwidth issue here now?
Say it loud.
I was wanting to know. We know that there can be a lot of simple organisms out there, but is there how many civilizations, like how many intelligent civilizations like ours is out there, and how many can right now have the possibility to visit others? And are they peaceful to us, or are they going to be warlike? Like
now, that's
like
an interesting question.
Okay, let him answer now. You can try and answer that one. Good luck.
Yeah. No, that's okay. What was his name?
This is Brian.
Okay, Brian, I wanted to share with you that you're demonstrating quite a bit of intelligence here, because one of the things that we do concern ourselves with is, in fact, whether they're going to be friendly or not. And we do not know whether they'll be friendly. This is the risk you take when you choose to explore. Now, as far as how many civilizations can be intelligent, you know, we have to go by something called statistics, where we actually say, basically it's a guess. We have to guess how many might be intelligent. We might find, like I said, oxygen in a planet's atmosphere, and if we find oxygen, and then we know that it's probably being reproduced by life. But as you pointed out, how do we know it's intelligent life? We don't. What kind of signals are there that we might get that indicate something is intelligent? Well, maybe we would see some type of electrical interference, or we might see some type of visual indication from another planet that something different was going on than we understand within the world of astronomy or physics. There's a lot of things that we could talk about that would indicate potential intelligence, but not one of those things can indicate whether they're going to be friendly or not. But, you know, so Brian, that's a very good question, and I'm glad that you were able to sit and watch this talk.
Out here.
What's that?
Is that it?
Well, that's it for me. I finished answering. I don't know. I can't hear Morgan, though, if he's talking.
I don't. We're out. We don't have anything else here. Morgan, do you?
Oh, he says he got audio. Well,
Okay.
all right, Rich.
Hey, Mark, thank you.
Thank you, Rich, for having me at your meeting in Alabama, Huntsville, right?
Yep. And,
yeah.
Yep. The fact that you put some models down here, we're all going to now run over the Space Center and take a look at them.
Well, yeah, they're hanging from the ceiling.
Again, thank you for your time, Mark. I really appreciate it.
Thank you so much.
Out here.
Okay. Bye-bye.
Bye.
Morgan, can you hear me at all? Just not if you can hear me. Is there anyone at home? I cannot hear you if you're talking to me.
Check.
Oh,
All right, we have a serious question from our crowd here. I know Rich had to go, and I'm glad they could make it. That was a great question by the young individual. But before we go for the day, serious question for you from the audience, of course. Everybody here would like to see your portholes.
Okay, welcome to the ship, folks. Okay, this is this is my office. That's my office door over there. Okay. There's my the ceiling has these girders, and there's a giant hook coming out of a hole in the ceiling, and there are the portholes. Those are the actual windows to the office over there. You know, I have rivets on the wall, and some of them are a little rusty, but But the whole point is, it's actually all just a movie set. This is all just fake. I do it because I do a lot of work with the Navy. So many times I'll do a project and then they'll come up and just sit in here and look around and just feel comfortable. It's like, but it's kind of fun. But I work here every day, and my shop is back there. Through the hatch door is the shipping area, and then beyond that is the actual workshop, far away from computers, where they can get all dusty and ruined. So, well, there it is. That's the office. And but I figure if I have to work here, it's got to look pretty cool, right?
Yeah, no, I appreciate that. It was just we know that you work in many different fields. One making, devices, props, and also with your business. Now, we lost audio as far as being able to hear you about the question that we asked about the future of ufology. I didn't know if you wanted to get into that or if you already answered it. So if you probably did, and we didn't hear it. But
well, Rich's group might have heard it, but if you didn't hear it, what I mentioned was that the future of ufology is something that you, Morgan, are involved with, and Morgan knows this, and this might be a setup question from him. I know it is. Because look at me scratching his chin. He's going, yeah, right, okay, you caught me. Exactly. The bottom line is, what we're going with this is this. MUFON has been a scientific organization. Now, we've occasionally deviated from the path and so forth, but with the Scientific Review Board, we're getting back on the path. It's actually an excellent direction. And to go along with that, one of the things that I'm involved with that I started outside of MUFON, but I want to bring into MUFON, is the creation of systems that will help identify UFOs using scientific platforms and instrumentation. You might think of it as a Skywatch system, but it's that and much, much more, because it's a set of linked systems that actually talk to each other, tell each other that there's this system here at the bottom of a triangle of 3, for instance, sees something and tells this one up here, go look over there. And so now you have 2 guys looking over there. And if the third one down here can see it, he's going to look over there. And then you have now corroborative data from multiple locations. And on each location, each of these instrument platters, or platforms, okay, that we call them, have multiple instruments on those. So we don't just get a visual image of a sighting. We have infrared, ultraviolet, and we actually have some radiation systems that we're looking at, where our gamma ray detector works already. So we have the ability to detect different types of radiation. And the whole point is we put together a science team, and I started this probably a year ago. And now we have about 4 or 5 top scientists, some of them former government scientists that actually worked on the first Predator drone, the Clementine lunar orbiter, the Mars rovers. We have a lot of people on board signed right on, and we also have high-end programmers that are willing to work with us. I have at least one. Morgan knows a couple, and the idea is that we're going to be able to build the system, hopefully in 6 to 10 months, have the prototype ready, and there are people out there willing to support such an effort. A couple of universities have expressed an interest in joining up with us on this, and we've already got partners in the camera, computer chip, and graphics industries, as well as the infrared camera industry. There's several major companies that are already our partners in this. So this is not just some guys in the garage building a little thing they think will work. This is a full-blown network of scientists, engineers, and people that are building the real thing. It's about time. And so that's where we're going. And so the future of ufology is going to be that we're going to have a networked system to be able to acquire data. So, for instance, in the mid-90s, 94 or so, out in the Santa Catalina Channel off California, there were over 200 sightings of UFOs appearing to leave and enter the water out there. Don't know if it was really UFOs because we didn't really have any data. We just had sighting reports and not really many photos at all to check. So one of the things we're going to do is we're going to deploy in that channel. But this is a system looking for UFOs. So we had to design a system that would also be seaborne. So we have a land system that I designed, and I have a sea system I designed. The sea system is self-charging. It uses wave action to charge its batteries so that its electronics can keep going. And the land side is actually going to charge its batteries a couple of ways. But the sea unit is going to actually be looking down for unknown submerged objects. And we're going to see what's going on in the ocean. And based on some of the wavelengths and some of the frequencies that we're looking for, we know that we'll be able to look pretty deep into the ocean. And the Santa Catalina Channel is actually quite deep. So that's one particular deployment location. We've got a dozen deployment locations. And we deploy in sets of 3 is where the goal is right now. And there's a lot of stuff I can't talk about yet because we're still working out some details, and I would hate to give you incorrect information. But everything I've told you to this point is correct. And Morgan is spearheading the MUFON involvement for us. He's actually going to probably lead that effort for MUFON. I would actually take a backseat to him on that. When it comes to the MUFON side, I'm going to let him do that. I'm working on the systems. I'm doing some of the design. All right, but I'm going to let Morgan run with it with MUFON once we get that up and running, because I think that he's going to be very good at that. Now, that doesn't mean that you folks are left out of this. You're not in any way, shape, or form being left out of this. The whole point of the data is that you have data, and you're going to be able to look at data. You're going to be able to see it. We would like to eventually make this crowdsourced, meaning we will have it on the internet, and you can log in and check it out, download this amount of data for this day or whatever, and see if there's anything interesting in there. In the same way that the SETI program had a little software program, you could sit there and just analyze SETI signals on your computer all you wanted. I personally don't believe in the SETI project, okay, and I'll tell you why. SETI was listening for radio signals, but at 100 light years, radio signals emanating from any place are going to be 10,000 times fainter than they are from when they left because of the way they attenuate over distance. That falls off over the square of the distance, meaning, if it's 2 times farther away, it's 4 times as faint. So because of that, SETI can only reach out a few light years, and that's okay. I mean, for that purpose, it's great. However, at 100 light years, and just before that, now those radio signals are only as loud as the noise already generated by stars and galaxies themselves, because remember, stars are generating light, but radio frequencies are light. They're just a different part of the spectrum. So the stars generate that too, the galaxy generates that, objects in space generate that. So we want that signal to be above the noise, and to get that signal above the noise, radio can't help us. Where we want to focus then is to look, like I was saying in the talk, for oxygen in an atmosphere. That we can find 1,000 light years away. So things like that are going to be helpful to us. Now, when we want to look at home, this project we're talking about, the UFO detection systems, are going to actually, we hope, be pivotal, because when you see a photo of a UFO, you're also going to have radiation imagery of all kinds, IR, UV, and we'll have all this corroborative data, even with just one platform. But if we get it with like 2, then we can calculate altitude, speed, distance, and get all kinds of things that we might not otherwise. And if we can get 2, for instance, then we can say, oh, it's a satellite, and we can just exclude it, right? We have a transponder decoder system that we're going to use on each platform, so that if we see something and 2 units on a triangle, 2 vertices of a triangle go, whoop, what's that over there we're looking at? They both get a transponder code from the thing, and they say, oh, 1200, that's a military aircraft. Okay, ignore it. So when we see a transponder come in, we know to ignore it. We're trying to cover all those bases because we're trying to actually get past all the knowns. Because what are we about? Finding the unknowns. And if we have an automated system that allows us to pre-sift out all the knowns, all we get are the unknowns. So we might go weeks without seeing a darn thing, and boy, we'll all be disappointed. But then we're going to get that one signal, and that one imagery, that one set of data. And we only need one smoking gun, folks. And I haven't told you some of the other units we have on board the system, but There's one particular that is actually going to be detecting the smoking gun. If we detect it, it's a 100% proof positive that we have an alien visitation with another ship from another place. So.
Turn yourself. Yeah. Okay. Well, that's perfect. Kind of gives people a little bit of taste of the future of ufology. I think science and technology is finally going to catch up to the speculative work that we've been doing in the field for a long time. And not that it's bad. It's actually been good to understand patterns, to understand locations, people's witness testimony.
Of course.
But I think that data, that scientific correlation is missing. And I think once that starts to connect with the qualitative data that MUFON has been, and some quantitative data, especially with radar data and whatnot, starts to combine with active investigative quantitative data, I think it's going to be a wonderful thing. And it's definitely the future of ufology, is combining those two and bringing technology up to where we are today. So
I agree, Morgan.
Well, I wanted to thank you for coming on, and we're going to go ahead and end the broadcast. And for everybody at home, we're going to keep trying to do these things throughout the year, and I believe this coming Monday we're going to try it again. So stay tuned. On Florida MUFON, we're going to continue to try to give you guys more content by these types of events. We wanted to thank you, Mark, for coming on and sticking through the frustrating first half and dealing with technology and how the problems that we always run into with computers and the new stuff. And Google Plus is still in its infancy, and it's still trying to work out the bugs, obviously. And but I'm glad you could come on. I really appreciate it.
Yeah, thank you so much. I'm glad we actually could do the combined meeting. That was a good test. So, neat.
All right. Well,
thanks,
we'll talk to you next time. I'm going to go ahead and end this, and if you can probably stick around just for a few minutes, but everybody at home, thanks for watching, and if you missed it, obviously this is on YouTube, so you can watch this on the YouTube channel because it will record it. So thank you again, and thanks for everybody coming in.